Hey everybody, this is Mr. Folly, and welcome to Big Idea. We'll probably just get through 1.5. Well, 1.5 through 1.8, and we get to learn a little bit about electron configurations, off-baud diagrams, Coulomb's law, and make sure you have your periodic table handy. So, protons and neutrons are in the nucleus, but electrons are arranged in clouds about the nucleus. Okay, so we're going to talk about this and maybe remember something that started a little 1s2 from first year chem, but we'll see. The largest grouping of electrons is called an energy level or a shell. An energy level is a shell around the nucleus. The energy levels correspond to the row of the periodic table, except D and F. So the energy level is shown by the coefficient of an electron configuration, right there. See that? Okay. The next letter tells you the shape of the orbital, like this right here. That can be identified on the periodic table. S is spherical. Spherical. P is dumbbell shaped. I don't know that I'd call that dumbbell. But D and F are just called complex because they're crazy shaped. Cray. There you go. Looking at the orbitals, you can see this is where the S orbitals are. This guy right here is also S. The D orbitals, the P orbitals, and then the F orbitals are right here. The next part tells you how many electrons are in that subshell, except for it looks like you have the wrong part circled. That would be this number right here. The periodic table shows us the limit for each. So if I'm looking at the S orbital, see I'd have 1, 2, S holds at most 2. P holds at most 1, 2, 3, 4, 5, 6. D holds 10. F holds 14. Okay, and you just count the columns. All right, examples, carbon. Let's take a look. Okay, so we've got carbon right here. So I'm going to start at the very beginning. Whoop. I'm in the first row, S block, and I've got 1 and I got 2. Takes care of 2 of the electrons in carbon's number 6. 3 and 4 are going to be second row, S block, 2. Again, 1, 2. Now I'm in a new block. I'm still in the second row, second energy level. Now I'm in the P block, and oops, I don't go all the way through there. Oh, I only have to go 2. Boom, that's carbon's electron configuration. Okay, so argon is next, and it looks almost exactly the same because remember, if I start at the top and move down, if I keep doing the same thing over and over again, it's going to be the same thing over and over again. So this first part, 1, S2, first row, S block 2. I'm going to erase that. I got a little sloppy. The next part, number 3 and 4, second row, S block 2. Whee! Still in the second row, P block. See, I'm in the P. 6. And I'm going to keep going until I get to argon, which is right here. The next 2 would be the third row, S block. See, I'm in the S. 2. There's 2 of them. And then I'm going all the way to argon, 3, P, 6. Third row, right? 1, 2, 3. P block, check. 1, 2, 3, 4, 5, 6. D's and F's have an oddity of the shell, oddity that the shell is 1 lower than the periodic table's row for D and 2 for F. So you know how this would be 1, 2, 3, 4, 5, 6, 7. This in the fourth row would be 3, 4, 5, 6. And then I think it's easier instead of thinking what it's compared to. If you're in this F block, it's 4. If you're in this F block, it's 5. So let's take a look. Titanium. Okay, so we've learned that these are pretty repetitive, so I'm going to go quick all the way to argon. I'm going to copy argon. 1s2, 2s2, 2p6, 3s2, 3p6. And that got me to 18. I now have 19 and 20, 4s2. And then remember, D's have to be lower 1. So when I'm in the D block right here, I'm not in 4D, I'm in 3D dose. Okay? Yeah, cerium. Oh, my periodic table's small. My eyes are bad. I got to find me some cerium. Ce is cerium. 58. Oh, no. Cerium is right here. Okay? Now, Your periodic table should, the one I stole from the internet, look like this. LA and T8. Well, it's LA and AC go here. So, cerium. That's going to be the exact same thing as titanium, but I'm going to stop right here. Okay, so I want to get to 4s2. So I'm going to copy this all the way up to here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then I'm going to start it up again. My 10s, 3, D, 10. Then I'm going to go over here, back to 4. So now that I jump back up, it's 4, P6. So notice I go from 4, only the D's drop down, back up to 4, 4P6. Now I'm at 5S2, 5S2. The next part of the D's, remember they're one lower, 4D10. And then the last part's going to be 5P6. And now I go from 6S2, and this is a squinter here. If we look really close, when you look at your periodic table, it goes cesium, barium, lanthanum, hafnium. And this is 55, 56, 57, 72. And you don't have to be an honors BC calculus of the greater Western world to know that all the way over here after 57 comes 58 is cerium. And you keep going. Oh, cerium's number 58. So what I have to do is account for, here's cesium and barium, this one right here, which is 5D1, and then I jump down to 4F1. Yikes. Okay. Next, we have a noble gas notation, core notation. Shortcut, yeah! So what you do is you pick the preceding noble gas in brackets, and then you finish the configuration. So I'm going to look at zinc. Erase up here. Zinc is Zn, and zinc, my friends, is right here. Noble gases are these right here. Pum, 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 pum. Those are your noble gases. So the preceding noble gas for zinc is argon, right? Zinc is number 30, if you're looking at your periodic table. The preceding noble gas is the one that comes before, which is argon, which is 18. So what I'm going to do, instead of writing everything for argon, I'm just going to write argon. And that takes me up to 18. So 19 and 20 are 4s2. And then I go to finish off zinc and 3d10. Pew, 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 pew. I think on your phone, if you write pew, it does little laser shots. I'm not sure, but I've heard that. Pew is number 94. So my preceding noble gas is going to be radon, number 86. Find those in your periodic table, 94 and 86. Then what we see is I've got to do 87 to 88. Oops, 87 to 88. And that's going to be 7s2. Then I got to do 89, which is all by itself, 6d1. Then I get to pew, 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 pew. Uh-oh, I lost pew. Oh, there it is, 94. And then I've got to do 90 to 94, which would be 5f, thorium, palladium, uranium, neptunium, polonium, 5. There you go. All right. So now we have why do the electron configurations work as they do. First, we're going to start with the off-ball principle. The off-ball principle says you start at the lowest energy, which is closest to the nucleus, okay? That's the most stable, okay? So if I said, oh, no, I don't feel so good, and I fall to the most stable position, boom, baby, I'm on the floor, all right? So it's going to start with 1s2, and it's going to go in order. That's how you tell if you're obeying the off-ball principle. The next one is Hund's rule, which is electrons spread out. Okay, so what that means is it can be messed up if you have bad arrows. But if I have 3D and I want to put 5 electrons into 3D, okay, so here we go. A box is an orbital that holds up to 2 electrons. So 3D holds 10 electrons, right? So that means it would have 5 boxes. 1, 2, 3, 4, 5. And because we live in a sharing world, if I had to put 5 in there, I would put 1 in each one. Oh, how nice it's sharing. Okay. That way it has the maximum number of boxes filled. I'm going to show you one that would be wrong here. If I did up, down, up, That would not be maximizing the sharing. That's not what helping Hund rule says. Hund says we love everybody gets one. Aw, how nice. And the Pauli exclusion principle says only 2 electrons can fit in an orbital. So that means I could not have an orbital like if I had an s orbital. I cannot have up, down, and then something else. That wouldn't fit. And those problems show up. You know, s can hold 2. That's okay. But if I have 4p, 8 can only hold 6. And that means you're breaking the Pauli exclusion principle. All right, this is best seen for the Hund's rule as an orbital diagram. So aluminum has 13 protons and 13 electrons, so I'm just going to put in electrons. Now here's my first batch of Hund's rule. Aluminum's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So as I fill this up, I do one at a time. Each orbital gets one because they're equal levels. And then 2, 2, 2. 3s has 2, boop, boop. 3p has 1. Okay. And notice I fill the lowest energies first. Easy enough. If it doesn't show up and down, it could be like vanadium, which is sideways. Vanadium ends in D3. When I look at the periodic table, here's vanadium. So this would be the 4th energy level. It's going to end in 3D3. So here we go. Vanadium. 1, 2, 3, 4, 5, 6, 7. Sharing. Aww. Filling them up. And keep going. 3p. Oh, look, look, look. Okay, down, down, down. 4s. Oh, look, I do up and down. Now 3d, I have 3d3. So 1, 2, 3. And this is important because single electrons form bonds. And that's a good one. Note 4s comes before 3d. And then I'm going to talk about valence electrons, and then we'll stop. So the valence electrons are outermost s and p electrons. The valence electrons are electrons involved in bonding. And the d block elements have 2 valence electrons. Those would be the s2. D's don't count as valence. So your valence electrons are your outermost s and p's. So for example, on vanadium, I would have 2 valence electrons. For aluminum, outermost s and p's, that's the 3rd level is my outermost level. That would be 3. And that'll do it for us. And I will say toodles.